Okay, this is Brian, and today we're going to be talking about traveling waves, and that is the stuff of chapter 15 in the textbook, and I want you to read all sections of the chapter. Okay, it's a short chapter, it's got a lot of good stuff in it, and I want you to get a chance to experience it all, and some of it we'll talk about in some detail. I'll talk about some of those things in the slides and also at our in-person in-session on Monday. And I'm starting with a picture of Milo for two reasons. One, he's got little sensors where he's picking up two kinds of traveling waves. One, he's got his eyes here, which he's picking up light waves, and then he's got his ears, and clearly he's sensing some sound waves with his ears. And so he's a great traveling wave detector. And actually, for Milo, and I know this from watching him in action, the ears are the most important thing. And so when he's got his ears up like that and he's turning his head from side to side, he's not looking around, he's listening around. And I'll talk about that a little bit later. Before I do that, I want to talk a little bit about problem 72 on the last homework assignment. And there's a reason for it. Okay, so when I was working with people to solve the problem, and this is the one about the orangutan motion, people said, oh, look, I'm looking for a speed. And so I just went through the chapter and looked for an equation that had speed in it. And you have one, but this one's not germane. In this case, you really can't use it here. This is the maximum speed. And so you could use that, although it's a little bit complicated, to figure out the maximum speed, the orangutan at the bottom of its swing. But that's not what you're looking for. You're looking for it's the actual speed of its motion, more of an average speed. And to do that, you want to think back to stuff we learned in chapter 2. And remember, we know that the speed of an object is equal to just the distance it travels divided by the time interval that it traveled in. And that's the relationship that I want to use to solve the problem. And what I want you to think about is this. And a lot of you are asking me, how can I do better in the class? I would like to be doing better. Here's my one piece of advice to you. As you're solving problems, worry more about your procedure than your results. Do you know what you are doing and why? And I really want you to spend some time thinking about that. You're learning how to use physics to model the world. Okay, that's what you're learning to do. And we're showing you lots of examples of this, and it takes a lot of practice. This is not a trivial thing to do. We're giving you lots of support as you do it, but fundamentally, that's what we're asking for you to do. So, for the case of the orangutan, what we wanted you to do was this. Start with a model, and we're going to say we're going to model an orangutan as a pendulum. Okay, and you can see it's like this orangutan has got his hand here, and his arm is working like a rope, and then he's working kind of like a point mass right here, and it's just swinging through an arc like so. And so an orangutan is a pendulum, and so we can model it that way. Second piece, we want to think about relationships, and the relationship that we're going to use to find the speed is the one that we have from chapter 2, this one right here. V is equal to delta x over delta t. Delta x I can find using trig. Delta t is related to the period, because if I have pendulum motion, I can say something about the period of the motion, okay? And also, I can, if I know that it's pendulum motion and I know how the orangutan is swinging, and so if it's fixed here, and the orangutan's down here, and then it swings to the side at a 20-degree angle, I can use trigonometry to figure out the distance that the orangutan has moved in this particular interval of time. That's what we were looking for you to do, and you can look at our posted solution. But I want you to think about this problem as an example of the type of how we want you to solve problems. You're applying models, you're analyzing the world, and don't just look for equations that you can stick numbers into. That's not what we're trying to show you how to do. We're trying to teach you how to use these models that we've developed to analyze the physical world. And one other thing we want to think about while we're on the subject of locomotion, I want to think about your walking. When you're walking and you're bringing your rear foot forward, so your rear foot is kind of like coming forward, it works like a pendulum. And so the frequency of the motion of your legs is basically fixed. And so when you're walking, and you saw this last week in lab, your stride frequency stays about the same. If you want to walk faster, you have to have a larger amplitude. You just have to take longer strides. And relating that to what we just saw with the orangutan, we said V was equal to delta x over delta t. Well, delta t is fixed by the pendulum frequency. To go faster, you just have bigger values of delta x. I just have to swing my legs farther. Now, I want to talk about wave motion, and I want to start by just reminding you you're supposed to read the chapter. So read chapter 15 and look at all these details we have in synthesis box 15.1. Lots of details. Wave speeds for the speed of sound, for the speed of light, for the speed of waves on a string. I want you to think about all of those. You have mathematical relationships for moving waves. I don't want you to worry too much about those, but I want you to know they exist. But the main things I want you to look at is this. Here's a picture of a wave at an instant in time, a so-called snapshot graph. Here's a history graph. This is a picture of the motion of a particular point in a medium as a wave goes by, okay? And as you can see, as the wave is going by, the medium is moving with simple harmonic motion. So the stuff we talked about previously in chapter 14 absolutely applies in chapter 15. We're building on it. The other piece I want you to know is this. There's a relationship between the speed of a wave, the wavelength, and the frequency. And it's this one right here. And this is the fundamental relationship for sinusoidal waves. And we'll use it quite a bit going forward. And so I'm just reminding you that here, V is equal to lambda times F. And I'll mention too, this is definitional. Okay, this is not like a law of nature. It's just based on how we define wavelength, frequency, and then speed ends up looking like that. Here, let's do some quick tests. So suppose I have pictures of waves, and I've got two different kinds of graphs I'm going to look at. This one, of course, is a snapshot graph, because this is the y displacement of the wave, graphed versus x. So this is a snapshot graph of a wave, and the wave is moving at 200 meters per second. First question, I want you to think about this. What is the amplitude of the wave? Go ahead and take 15 seconds to think about it. We'll be back. And of course, the amplitude is just how far are you from equilibrium? Well, the equilibrium position is right in the center, and the distance from equilibrium is just 1 meter. So the amplitude of this wave is 1 meter. Next up, what is the wavelength of this wave? Okay. Take some time to look at the graph. Pause the video. I'll be back. And the wavelength is just the distance between successive crests on the wave. And so it looks to me like that's going to be a distance of 2 meters. That's going to be 2 meters. Now, if this was a history graph, and so what we were plotting on this axis was not x, but the time in seconds, the distance between the successive peaks would be the period, okay? Next piece of the puzzle, what is the frequency of the wave? Take some time to think about that one. Pause the video. I'll be back. Well, in this case, what we need to do is we have to use our basic relationship for waves. We know that the wavelength is 2 meters. We know the speed is 200 meters per second, and we know that the speed is equal to the product of the frequency times the wavelength. So speed is 200 meters per second, wavelength is 2.0 meters, and so that means the frequency is just going to be 100 hertz. And that makes sense. That's 100 cycles per second. So as this wave is moving by at 200 meters per second, and there's a distance of 2 meters between successive peaks, a peak is going to hit me 100 times a second. That just makes sense. So that's going to be our answer for here. It's 100 seconds. Now I want to take a look at this problem right here. So I want you to pause the video, go ahead and take a second to read this slide through. Okay, now let's talk about this. And of course, the first thing we're going to do is strategize, okay? And this is the crucial information that was given in the passage. And so I've copied that here. The wave that produced this graph right here was traveling at a speed of 3,500 meters per second. We're looking for the maximum speed and the maximum acceleration of the ground during the passage of this earthquake wave. So first, how are we going to strategize? Take a second to think about that. Pause the video. I'll be back. Well, this is a history graph. This is a graph of the displacement of the ground as a function of time. So this is just a graph of the motion of the ground as a wave is passing. And if I look at that graph, I can see the graph is basically simple harmonic motion. And so I don't need to use any wave information at all to solve this problem. This is just a simple harmonic motion problem. And if I had said, here's a graph of simple harmonic motion, go ahead and tell me what is the maximum acceleration and the maximum speed, you know how to do that. You just have to extract information about the frequency and the amplitude from the graph, and you can use that to do that determination. And so I'd do that. I would say, look, the amplitude is about 60 centimeters. Okay, that's what it looks like to me, because that's the furthest the wave is from equilibrium, and that happens on a negative peak, but that's okay. We want the maximum possible amplitude. And we can look at the period as well, and let's just look at the time. So 1 cycle, 2 cycles, 3 cycles, 4 cycles, 5 cycles, 6 cycles in 60 seconds. The period is 10 seconds, which means the frequency is 0.1 hertz. With that information in hand, we can solve as we did with the simple harmonic motion problem. And you might do that as a practice. And if you do, these are the results that you get. You get the maximum speed as 0.38 meters per second. The maximum acceleration is 0.24 meters per second squared, which you would notice. It wouldn't be scary, but it would be kind of like something weird just happened when this thing went by. Now, let's take a look at this problem right here. Instead of a wave in the ground, which is an earthquake wave, let's look at a wave in water, a wave in the ocean. Okay? Take a second, read this problem through, pause the video. I'll be back. Now let's take a look at what this is asking. Okay, so an ocean wave is going by, and the waves have a wavelength of 190 meters. That's actually typical for waves in the open ocean, traveling at a speed of 14 meters per second. Again, a typical value. The top of the crest of the waves is 2 meters above the bottom of the troughs. Again, typical values. And I wanted to just mention, I spend a lot of time trying to get numbers that are realistic, so that when you end up solving a problem, you end up getting a number that tells you something about the world. So when this wave passes, the boat bobs up and down. And of course, the boat bobs up and down with simple harmonic motion. Oh, I'm getting ahead of myself. Let's just parse the problem, think about what it's asking, then go on to the next phase, which is strategize. So first we're going to strategize. And I'll say this. The motion of the boat as the wave is going by is just simple harmonic motion. So I have a wave like so. There's a picture of my wave. It's traveling at a speed of 14 meters per second. If I have a little boat, kind of like right here, so here's my boat, and it's bobbing up and down on the waves, it's going to basically be moving up and down with simple harmonic motion. Okay? And to be able to describe the motion with simple harmonic motion, well, I'm getting ahead of myself. That's really a prepare thing. So let's go to the next slide and think about preparation. So to prepare, what I'm going to do is this. Okay, so here's my wave going by like so. And I got my boat on top of this little wave right here. Okay, and the wave is moving at a speed of 14 meters per second. If I'm going to solve this simple harmonic motion problem, the two pieces of information I need are 1, the amplitude, and 2, the frequency. So let's think about the motion of the boat. And we're told that, let's see, the top of the crests is 2 meters above the bottom of the troughs. So when the boat moves from its highest point to its lowest point, okay, it's moved by a total vertical distance of 2.0 meters, which means that it is 1 meter above the equilibrium point and then 1 meter below the equilibrium point, and that tells me that the amplitude of the motion is 1.0 meters. And how about the frequency? How are we going to get the frequency? Oh, well, I know the speed of the wave, that's 14 meters per second, and I know the wavelength of the wave, okay, that is 190 meters. So with those two pieces of information in hand, I can calculate the frequency by this equation. V is equal to F times lambda. And with that in hand, we're ready to do some solving. So we're looking for the motion of the boat, that's simple harmonic motion, and we know that the amplitude of the oscillation of the boat, okay, we know what that is 1.0 meters, and we can find the frequency by saying v is equal to f times lambda for the wave. So f is equal to v over lambda, so it's equal to 14 meters per second divided by 190 meters. And then for simple harmonic motion, the maximum speed is equal to 2 pi times f times the amplitude. The maximum acceleration is equal to 2 pi f squared times a. And we have all the information that we need in hand to solve those because we can calculate the frequency. And with the frequency in hand and the amplitude in hand, we can calculate these two expressions. If we do that, we get these values. For the maximum velocity, or the maximum speed, 0.46 meters per second. The maximum acceleration, 0.21 meters per second squared. That's about 0.02 g. That is enough for nausea. And if you're in a boat on the open ocean and the boat is bobbing up and down, you are going to, if you're me, you're going to get nauseous. I definitely am sensitive to that, okay? And so that seems reasonable. I have been in a boat on the open ocean and gotten real nauseous. So this makes sense to me. Now let's take a look at this problem right here. Okay, so this is another wave problem. I want you to take a moment, read this one through. So pause the video, read the slide through. We'll talk. Okay, now here's what I want you to do first on this problem. This is the kind of thing you should be doing in general. Now, for our strategize step, I want you to just pause for a second and describe in words how you will solve this problem. What are you looking for and how will you find it? So just pause for a second. Think about that. Pause the video. Think about what you're going to do. Then we'll talk. Well, there's two different waves that you're asked about here. One is a sound wave that's going to travel through the air, and the second is a wave on the web silk. So I want to know which is greater, the speed of the wave on the silk or the speed of sound. I want to know which is greater among these two things. Whichever has a greater speed is going to get there first. And so we're just asked basically to figure out the two different speeds. Now next up, we're going to prepare. And for a prepare step, we'll just say this. The speed of sound in air, we're going to use a value of 340 meters per second. Okay? So we're just going to have to compute the speed of the sound on the silk. Now for the speed of the sound on a silk, okay, that is determined by our equation for waves on a stretched string. And that speed of a wave on a stretched string was equal to T, the tension, divided by mu, which is the mass per unit length. Okay, that's the mu. That's my preparation step. Now the tension we're given, that's 7.0 millinewtons. The mass per unit length, I'm just going to do this. I'm going to figure out the mass of the string, okay, and then divide it by the length of the string. And let's just assume, to make things easy, that I have a 1 meter length of string. I can assume that. And since I'm not told anything about the length, I can assume any value I want. That's something you're always free to do. So let's just assume it's a 1 meter length and see what we're going to get. And the mass of the string is just going to be equal to the density times the volume. Okay? Now, and the volume, because we're going to assume if it's a length of string, it's going to be basically a cylinder. It's got a length L, and the cross-section area, of course, is pi r squared. And so the volume is just going to be equal to pi r squared times L. We have everything we need to go ahead and do a solution. And when we do that, we're just going to complete our calculation. We're told the velocity or the speed of sound on the web silk. That's just the speed of sound on a stretched string, or the speed of a wave on a stretched string, t over mu. T is equal to 7.0 millinewtons. Mu is equal to m over L, where m is equal to the density times pi r squared times L. And then I divide by L. Oh, heavens to Betsy. I said to assume a length of 1 meter, but it turns out I don't even need to worry about that, because if I stay symbolic, that actually goes away. And so I have everything in hand that I need. I can put the numbers in. If I do that, I get a speed of the wave on the web silk of 430 meters per second. That is, in fact, bigger than the speed of sound, which is 340 meters per second. And so the wave on the silk gets there first. My assessment is that seems reasonable, because if an insect lands in the silk, I want the spider to know about it quickly. And so I want it to be comparable to the speed of sound in air, maybe a little bit greater. So the spider gets the news first before the insect knows the spider is coming. And that number seems quite reasonable. And I want it to be slow enough that the spider is able to tell where the insect is. And what the spider does is it monitors vibrations on different parts of the web and sees which one gets to it first. And it uses that to determine the exact location of an insect on the web. And in fact, you do something like that too. You locate where sound is coming from by looking at the arrival time of sound at your ears. If I have a sound source over here, it gets to that ear before it gets to this one. And you measure that difference in arrival times in order to locate the source of the sound. And you're better at it if you put your hands behind your ears like that. You get a much, much better sound locating ability. And if you do that, put your hands behind your ears like that, you can listen around and you can tell very precisely where the sound comes from. And that is what Milo is doing when his ears are up like this. He is listening around and he's cupped them so that they're picking up the sound from the forward direction. Sound gets to the two ears, and he measures the different arrival times. And so he's able to tell exactly where a sound is coming from. He's really, really good at that. Now, I want to talk about another property of waves, and that's intensity. Intensity is generally a ratio of power to area, and power is in watts, and area is in meters squared, and so intensity is watts per square meter. And we'll look at an example in the in-person class of how we would calculate that. But I want to rearrange that equation and take a look at this. If intensity is power divided by area, the power is equal to intensity times area. Now, a sound wave has a certain intensity, but what you detect is sound power. How do you detect really, really faint sounds? If you have a lot of intensity, so this number goes up, the power goes up as well. And so if you want to detect very faint sounds, i.e. very low intensity, you want a lot of area. So bat-eared foxes have bat ears. They have really, really big ears. Big area captures a lot of intensity. Or in the old days, if you were hard of hearing, you could have an ear trumpet, which just expands the amount of expands the amount of area that is capturing intensity. Or if you're the great gray owl, its ears are actually on the front of its face, and it's got a structure like this. And this is basically an ear with lots of area, and so it can capture lots of power, which makes their hearing exquisitely sensitive. Now I want to think about the intensity for a spherical wave, okay? So if I have something like the sun, which is a sphere, and the sun gives off waves, light waves specifically, as you go further and further from the sun, the intensity drops off, and the relationship for the drop-off of intensity is just this. The intensity is equal to the power of the source of the waves divided by 4 pi r squared. And r looks like it's a radius, but really what it is just a distance. It is the distance from an object that's emitting a spherical wave. And since it's a spherical wave, we physicists use r because r is kind of a sphere thing. But really, this is just a distance. So I want to think about this problem right here. At the Earth's surface, the intensity of sunlight is about 1100 watts per square meter, okay? And the Earth, by definition, is 1 astronomical unit from the sun. If you're at the distance of Saturn, which is 10 astronomical units away, what is the approximate intensity that you will have right there? And I want you to solve this problem But just looking at ratios, just using ratio reasoning, and that's a useful thing to be able to do. So go ahead and pause for a second. Think about this equation. Think about how the intensity will change if I change the distance. Take a minute, work that out. I'll be back. Here's how we'll solve this. We have this basic equation right here, and we're told that the distance goes up by a factor of 10, because I've increased r by a factor of 10. But what appears in the denominator is r squared. If r goes up by a factor of 10, r squared goes up by a factor of 100. And since r squared is in the denominator of this fraction, the intensity is going to decrease by a factor of 100. So instead of having 1100 watts per square meter, as you do at the surface of the Earth, at the distance of Saturn, it's only 11 watts per square meter. So you have very, very low intensity of sunlight out at Saturn. And in fact, that's why when you send a probe to Saturn, you can't run it with solar power. There's just not enough. Think about this. At the surface of the Earth, 1100 watts per square meter. So a square meter solar cell will capture 1100 watts of power. And if you convert that at 20% efficiency, which is reasonable, you're going to get a couple hundred watts of power. But if you're out at Saturn, you're only getting 11 watts per square meter. 1 meter square solar cell, 20% efficiency, you're getting just over 2 watts. That is not enough. So in fact, probes that go to Saturn and distant planets are typically powered by nuclear power. That's the only way to make those go. Now I want to talk about something related to sound intensity, and that's the idea of sound intensity level. And I'm going to talk about this at some detail in class. And it turns out that the range of intensities that your ears are sensitive to spans a factor of 10 to the 12th. It's a factor of 1 trillion, from the loudest sound you can comfortably hear to the quietest sound you can hear. And so as a consequence, we use this decibel scale. And sound intensity level in decibels for sound of intensity I is this expression right here. It's given by this expression right here, and it uses logarithms, which you've learned about in a previous math course. If you have to go backwards from sound intensity level to intensities, you can use this relationship right here. Now, the I0 that appears in this equation is the lowest intensity you can hear. That's 1 times 10 to the negative 12th watts per square meter. Now, I want you to think about that. That is 1 trillionth of a watt spread over a distance of 1 meter. Okay, so imagine that. 1 trillionth of a watt, and you spread that power over the distance of 1 meter squared. That is a ridiculously small intensity. Your ears are insanely sensitive. Now here's a table of values of sound intensity levels, and I want to show you something about how this works, and this is from the textbook. Your threshold of hearing is 1 times 10 to the negative 12th watts, and if I put that number in the equation, I get a sound intensity level of 0 decibels. If I increase the intensity by a factor of 10 to 1 times 10 to the negative 11th, the sound intensity level is 10. If I increase it by another factor of 10, 1 times 10 to the negative 10th, I get 20 decibels. So each increase in power by a factor of 10, or intensity by a factor of 10, corresponds to an increase in sound intensity level by an additive factor of 10. So from 20 decibels to 30 decibels is an increase in intensity by a factor of 10. From 30 to 40 is another factor of 10, and so on. So going all the way from 0 up to 120, that is a factor, that is 12 factors of 10, 10 to the 12th, or 1 trillion times the intensity. Okay, over that range. So your ears are sensitive over a dramatic range of intensities. Now, I want to do some calculations with sound intensity level. And here's my first one. Okay, yelling as loud as you can makes a sound intensity level of about 1 decibel at a distance of 1 meter. So here's my question. What is the total acoustic power that you generate when you're shrieking at the top of your lungs? Okay, I want you to first think about this. How are we going to strategize? Take a second, think about it. I'll be back. I'm going to assume that when you're yelling, basically the sound spreads out evenly in all directions. So I'm going to assume that you're emitting a spherical wave. Okay, I'm assuming you're emitting a spherical wave. And we're given the sound intensity level, that's 110 decibels. Well, I want to convert that to an intensity because the intensity is the physically reasonable one. And there's two ways to do it. But to do that, that sounds more like preparation. So let's go on to the next slide and talk about that. Okay, so we said we're assuming it's a spherical wave. We're told it's 110 decibels. And if I take 110 decibels and I want to convert that to an intensity, one thing I can do is just look it up on a table. If I look it up on a table, that's 0.1 watts per square meter. But if I don't want to do that, I can use our basic relationship. And our basic relationship says the intensity is equal to I0 times 10 to the power of beta divided by 10 dB. So in this I0, of course, that's the smallest intensity you can hear. That's 1.0 times 10 to the minus 12th. And I multiply it by 10 to the beta, which is 110, divided by 10 decibels, so 10. So 1.0 times 10 to the negative 12th times 10 to the 11th is equal to 1.0 times 10 to the minus 1, or 0.1 watts. Well, that wasn't a very good W. Watts per square meter. Okay, so that is our intensity. That is the physically meaningful thing we want to use. And then we're going to use that intensity in our basic expression, which talks about how intensity varies as a function of distance from a source. And the intensity is equal to the power of the source divided by 4 pi r squared. Okay, next slide talks about solving. So we'll take that equation where we say the intensity is equal to the power of the source divided by 4 pi r squared. And we'll notice a couple of things. One, the intensity is 0.10 watts per square meter. The distance, r, is 1.0 meters. That's how far away you are from the person who is shrieking. What I'm looking for is the power of the source. And with all that information in hand, I can go ahead and calculate. And if I do that, I get 1.3 watts. Okay, and that's reasonable because I've said your ears are incredibly sensitive. 1.3 watts is not very much power, but your ears are incredibly sensitive, and so that will actually sound quite loud to you. Now, something else I want you to think about is this. If you're doing an output power of 1.3 watts and we assume an efficiency comparable to your 25% efficiency, which we've assumed for different XTs, that corresponds to a metabolic power of 5.2 watts. So 5.2 joules per second. So shrieking at the top of your lungs is not a very, very good way to burn off calories. In fact, if you're like my family and after Thanksgiving dinner you get into heated arguments, if you want to like burn off the calories in your Thanksgiving dinner, you're gonna have to yell continuously at the top of your lungs for 12 days straight. And if you're my family, that might be something that is within the realm of possibility, but not the best way to kind of achieve this goal. Now I want to talk about briefly the idea of the Doppler effect. If I have a moving source of sound waves, the frequency from it varies. The frequency that you observe varies, and it depends if it's moving towards you or away from you. Okay? And if I have sound that's reflected from something that is moving, I get a shift in frequency due to the reflection, which is using this relationship right here. Now, this is really important for a couple of reasons. One, you've seen Doppler radar. And Doppler radar, they bounce radar, which is basically electromagnetic waves that move at the speed of light, off of storms. And if they do that, they can tell where the storm is, but they can also tell how it's moving, which is kind of awesome. It bounces off individual raindrops. But here's a little Doppler radar picture off the southern tip of Florida. And what is here isn't a rainstorm. It's actually birds. And this is a gigantic flock of birds that was sort of migrating. And one of the things that people have observed with now that with the use of Doppler radar is that you will see migrations of birds or insects and all kinds of things. There's a lot of other things that people have learned about the world by doing this. Now, another thing you can do is you can do Doppler ultrasound, and if I do Doppler ultrasound, the ultrasound images tissues inside your body. But if I also record the frequency shifts, I can record motions of moving objects, and so I can see I'm doing an image of inside a person's body, and I can see tissues that are moving toward or away from the detector, which is kind of awesome. And I had a chance to do this recently. I had a Doppler ultrasound scan of my carotid arteries, and you can see, like, here's the blood in my artery. And the technician, and she was great, she gave me all kinds of data about what she was doing. She was using a 3.5 megahertz beam of ultrasound, way beyond the frequencies that your ears can hear, so that's why it's ultrasound, and measured a speed of 109 centimeters per second. That was a peak speed for blood in my carotid artery. And so here's my question. For that case, what was the frequency shift? What was the frequency shift? And the frequency shift is just given by this expression right here. Now, in these problems, okay, the important thing is going to be that you have to know what the different terms correspond to. This right here is the original frequency. My O and my 0 look the same, but this is the original frequency. That's 3.5 times 10 to the 6th hertz, okay? This here, VO, that's the velocity of or the speed of the object. That's 109 centimeters per second, or I have to put it in meters, of course. So that's going to be 1.09 meters per second. V is the speed of the wave, and for ultrasound in human tissue, that's 1540 meters per second. And then there's a plus or minus, and the plus or minus just says you get a shift that's to a higher frequency if the object is moving closer to the detector, and you get a shift that is lower in frequency if it's moving away. And it turns out I really don't care, so I'm not going to worry about the plus or minus. But with all those numbers in hand, I can calculate a frequency shift. And what I get is a change in frequency of about 2,500 hertz. So actually, when they were doing this, that they turned it into an audible signal, so I actually hear it, and it would go like, pew, pew, pew. It was kind of an awesome experience. Really, really enjoyed that. One last topic I'll bring up is this. If something is moving through a medium faster than the speed of the waves in the medium, I get a shock wave. All the waves basically pile up, and I get this shock front. And you can see this Milo is swimming through the water, and all of the waves that he is making in the water are piling up, and it makes this little wave front that he's kind of like pushing through the water as he's bringing a stick back to me. Or a bullet moving through air is moving faster than the speed of sound, and so all the sound that it's making as it's going through the air makes this shock front. And when this passes you actually hear a crack. It's like a little sonic boom as the bullet goes past you. Ducks can swim faster than the speed of sound or the speed of waves in water, and so they leave a wake behind them. And if it's a narrow wake, that just tells you that duck is really cruising. The duck is really, really cruising. But that's basically a shock wave, and all the waves that it's creating kind of like pile up like so. And there are places where you get this, and you get it you get this sort of like shock wave when something's moving faster than the speed of sound. That is actually the reason why a whip will crack. The tip of the whip is actually moving faster than the speed of sound. And so you got a little bit of a shock wave from the tip of the whip, which is kind of an awesome thing. Next piece of the puzzle, I want to talk about how you make and how you interpret sound. And it has to do with traveling waves, but also superposition and something called standing waves. And we're going to take a look at that in the last week before fall break, and it's got amazing applications to biological systems, and I'm just going to bring up one. So when Milo meets other dogs on the trail, frequently he will come up to them and give kind of a low growl, and he's not actually growling at them. What he's doing is he's advertising how big he is. And it turns out other dogs can very, very easily tell by listening to the first dog's growl how big they are. They're very, very good at that. And exactly how that works relates to standing waves and formants and all kinds of stuff that we'll get into next week. Thanks very much.